Hey everyone, I'm Brock Boudreau.
I'm Grant Armstrong.
I'm Nick from recording. I'll be back later.
And this is our Impact Project presentation. So this Impact Project required customer request. This model needed to provide time-resolved acceleration, velocity, displacement, and force. It must be easy to train new users to use the model effectively and safely. It must create a high signal-to-noise ratio. It must collect at least 10 data points in a measurement pulse, and it must match peak impact magnitude at 5% average.
All right, for the House of Quality. Here we have our customers. We have the professors, the university, and the students. And these are all of the customer requests. As you can see, we have them all listed out. This is going to be all of the, the accountability summaries, the sales price. This is how all of the customer requests correlate to each of these criterias. And also right here, we have our competitors. These are who we are measuring our device against. Like, we need to do better than these people. We need to beat them at their own game. And down here is also our competitors, and this is how they did on some of the criteria. Okay, and these are the first two apparatus that we designed. This is going to be the box catapult. It's pretty similar to what we have now, except basically how it works is you have the set apparatus, and you have this piece right here, which is the box that holds the phone. And these two items right here are rubber bands. What you do is you put it on the wall, you pull the box back, let it go, and then it's going to slingshot the phone into the wall, creating said impact. Now, that's not what we wanted, because we wanted our apparatus to create its own impact. So we decided to move on from that design. The second design is the two-phone pendulum. Essentially, you can, if you can't already tell, it's two smartphones. You kind of pull them both back, let them go, they hit each other, creating the impact. We just decided to go with it in another direction for this one because they required two phones and two readings, so it's probably going to be inconsistent data if both phones are recording. Okay, and this one, in my opinion, was probably my second favorite besides the one that we already did. This is the fall with the force pulley. See? It's an elevator, essentially. And what you do is, you see the box right there, it's on a string on the idle roller. And as you know, in an elevator, it's counterweights, right? But in my engineering brain, I decided instead to tension a gear, or essentially what is a spring, like gear, to kind of spool up, hold force, and then once you let it go, it's going to shoot off and drop the box onto the phone. All right. This right here is our current design. So it's like the wall, kind of like the wall catapult before, except here we have a foam block on the bottom, and it's right side up instead of sideways. And what you do is this part when it's idle, it's just going to be on the ground. What you do is you pull it back, it tensions these two rubber bands, let it go, it's going to create a nice impact. And that's what we went with.
So the decision matrix it was measured on a scale from 1 to 5, being 1 the worst and 5 the best. Out of all of our designs, obviously the fall of force placed first with the best points. Then we had the pendulum in second, and then the pulley in third. Basically, these are all of the ratings we gave. The Fall of Force, in our opinion, had the best impact out of the other models, and that's why we went with this design. So the solution, I'm going to bring the model in camera here. So we chose, obviously, the Fall of Force mechanism. In simple words, you pull rubber bands back, clamp them together. This is the Fall of Force mechanism. What you would do is you would pull the rubber bands back with the box attached, and you would clamp them down. And to release the tension, you release the clamp. The rubber bands will retract and hit the phone block. And this mechanism is supported by these dowel rods. The rubber bands obviously putting tension on the box. The hot glue supporting the dowels down here, which hold the rubber bands. And popsicle sticks to create a border for the phone block.
Yes,
To
right
give it
here
some-
we have the car. The car is essentially where we hold the phone. We have two foam pieces in here now to kind of secure the foam. It's held together with these rubber bands. And as you can see, the mounting points right here and here, they hold the rubber bands, and that's what is putting tension on the car. And it's going to correspond with these two, pull it up, with these two mounting points right here.
Okay, the first build was not what we were looking for, essentially. One, its appearance is not the prettiest to look at. And as you can see too, it's not really sturdy with these popsicle sticks holding it up. The release mechanism was not essential. It would release and create inconsistent data points, as you can see up here. It was just really hard to hold it in place, one, tense the rubber bands, and then release it. So therefore it did not perform well, and it was not symmetrical at all. It was just overall just a bad design. And this is our final build, which I will let Nick explain.
So he explained it previously, for the most part. But essentially, one thing we had to do, we had to add zip ties to the top so that we could actually clamp onto the clamp could grab it. Yeah, so the foam block would go here, but we do not have that today. So we will test it, but without the phone, so that no phone gets harmed in this process. We don't want that to happen. So we will now go to the test.
Hello, again, I am Brock Boudreau.
And I am Nick, and Brock is going to show you how to do the test. He has never done this before. I have showed him how to do it twice, so this is going to show how a novice user can effectively do this and get good results.
So the first thing we're gonna do is set up Firefox, which tracks the acceleration and all your data points. And you will record this by putting your phone into the case as shown here. To open the case and insert your phone, you're gonna take off both rubber bands. You're gonna slide your phone in here. This is the case we built, and there's two sponges cushioning the phone. So once the impact is created, the phone stays safe. I'm gonna put this rubber band back on. And we are gonna test this, but first, for safety, I will put on the safety glasses. Okay, so once you have the case clamped at the top of the model, you will then connect your rubber bands, as seen here, to these dowel rods at the bottom of the model. I'm gonna do that for you right here. It's better to go in a cross diagonal way first to secure the model in its place, as shown. And then you're gonna double rubber band the dowels at the bottom. This is to create a higher impact, putting more tension on the box up here. As shown. And now I will test it. As you can see, there's no foam block in here because we had to return it. So we're gonna do a test without the phone in the box to ensure safety and make sure that the phone is not broken. I will then hit the clamp and then the box will drop, creating your impact, as shown. So obviously this is our final build, and we showed you how to use our build in the video before. So I will explain what we did to fix our original model to the final model we have now. One, it looks a lot cleaner, a lot more presentable. It was a lot sturdier with these dowel rods and popsicle sticks for the foam block. It had a more reliable mechanism for releasing with this clamp, so it would hold the case at a consistent point every time. And it fit well with the foam block. Like I said, we built this box down here to fit the foam block so it would not move and create that impact and also cushion it effectively. So this is a fusion animation of our model here. As you can see, there is a couple differences in the model compared to our final model because this was an earlier build of the final model, but we had to make fixes for it to work effectively. This bill of materials, we used popsicle sticks, dowel rods, a pack of rubber bands, mini hot glue gun, a pack of hot glue gun sticks, a clamp, spray paint, and rope. As you can see, the total cost was $50.39. It's a little pricey. The reason why it was pricey though was because some of these materials were for the original model and not the final model. And we spent more to increase the efficiency of the final model. So the cost would probably have been around like half this amount. So it's really cost effective, not too expensive and easy to create.
Okay, so this is test one, and we're going to go through the data real quick. But for each graph, it is going to be time on the x-axis and then the impact on the y-axis. The graph organization's a little bit different each slide, but I will say which one's which. This one's velocity, newtons, acceleration, displacement. Test two, as you can see, all the graphs are pretty similar. So this is displacement, velocity, newtons, and acceleration. They're a little bit different or organized, but all pretty consistent so far. Test three, and this is our last one. So displacement is a little bit different on this one, a little bit of an outlier, but the data still lined up pretty well, so it didn't go too far away. Okay, so for the peak values, we took the peak value for each impact, so acceleration, velocity, displacement, and force, and then we took the average, and then 5% of that average is what this number is, and that is basically subtracted from each of these. Should be close to this, should be pretty close. It cannot be further. So the data was recorded through Firefox. We used a phone and a computer so we could have accurate timing. But to shorten the noise, we cut out, so basically we only recorded from 0 seconds to 0.2 seconds. So that way we didn't have any extra noise at the end to mess up with all our values.
And our conclusion, so our biggest success throughout this entire experiment timeline was coming up with the different models for this impact project. We all brainstormed concepts and collectively came up with the idea of the force fall mechanism being the best. The only challenge we had was positioning of the dowel rod at the top, as you can see. The reason why was these dowel rods were support beams, and if we made it parallel with these other dowel rods at the top, it would break the model because these are nailed in and these are not as much as support beams. So we decided to line it up across these two and place a clamp on here to produce the most strength. This will conclude our impact project.
Thank you all for listening, and yeah, that's all.